microphone on. Hello, I have turned my microphone on. Greetings, greetings, greetings. How is everybody doing today? I hope well. We've got 30 people in our television audience today. So, yeah. If somebody would please indicate that you are alive in the chat, I would appreciate it. And the first person to select a hue today will have they'll win the wonderful prize of seeing their professor in that hue for the duration of today's lecture. I will do my best. So, other than that, we might as well get straight to the point and resume our discussion of pointers. Oh, he's actually starting. Oh, here we go. Only on the outside. Yes. Could we go over the double pointer example? Yes, so, pardon me. Both Parker and Soroush should have done the double pointer example in their tutorials, but yeah, that's very fair. Double pointer example. I might even lead with that. You guys want me to lead with that? Maybe I should lead with that. Okay. I have decided. I will lead with it. So, let's get it. Double point dot, see? Okay. Enthusiasm. Nobody's picked a color yet, though. So, include stdio.h int main dup doop dap bap dee dow. Alright. So there's a slight conceptual difference between a double pointer in the sense of I'm changing the address of, like, there's double pointing in the sense of the address of an address. That's sort of linear double pointing. This is something that we'll see in the next set of slides when we start talking about pointer operations, because one of the things that not pointer operations, string operations. There are some string library functions that allow you. Basically, they are allowing you to have strings returned as implicit return values of functions, and in order to have an implicit return value of a function, we of course need a pointer to that. But since a string is a character pointer, that's a pointer to a pointer. The way that it's being used in the assignment is a different sense of a double pointer. In that sense, we are allocating an array of pointers. Each of those pointers points to something else. It's much more similar to the case in, I think it's in somewhere with the card suits. Yes. So the double pointer example is actually a lot more sort of close in. It works like this, figure 7.22. You have an array of pointers, and they each point to a different segment of memory that contains a thing. That thing, in this case, being character arrays. But it doesn't have to be character arrays. It could be integer arrays. It could be struct arrays. It could be any number of things. Yes. So, Nice hot pink. Coming right up. Nice hot pink. I think I might have to buy a new camera. That's audio properties. What are you doing, man? I might have to buy a new webcam at some point, because, like, the default setting, you see how I've got the brightness and the contrast turned way up here? This is what I, like, woke up to my my camera looking like yesterday, so that's reasonable. So, pink, 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 pink. Turn up the saturation. Ooh, okay. That, yeah, we want hot pink. That's hot pink. Okay, there we go. I look like a Kirby. There we go. Actually, no, Kirby's a little bit of a softer pink than this. Oh well, we'll call it a Kirby. There we go. So, anyway, so the array of the array of pointers is really the concept that we're going for here. But of course, an array of pointers is a pointer to a bunch of pointers. So, let's use integers just for fun. So we have a double pointer. Double pointers have 2 stars. Triple pointers have 3 stars, etc., etc. We'll call it matrix. Sure. Although matrix implies it's square. We don't want to imply it's square. Let's say it is, I don't know, array. Let's call it foo. There we go. Let's also indicate a number of foos. So, let's say we'll make it 10. So, the first thing that we have to do is let's dynamically allocate to foo the size that it needs for all of the integer pointers. So, foo is equal to malloc. N times size of integer pointer. There we go. Now, of course, malloc fills that with junk data, smelly, smelly garbage data. So, in order to actually have those be actual pointers, we need to go through each element in the array and make each of those elements, each of the values in the array, the results of their own malloc calls. So, for I equals 0, 0, I is less than n, I plus plus, let's say that foo at I is equal to, and just, you know, just for the sake of simplicity, let's actually make this a rectangular. So this is actually a matrix. The advantage of this technique versus just using a two-dimensional array is that it doesn't have to be. You notice here that each one of these elements, it's like ragged, right? They do not contain the same number of elements. They don't have to. The memory has been allocated separately for each one of these elements. Therefore, they don't have to be the same size. However, if you were to use a two-dimensional array, they would have to be the same size. That's how arrays work. You need to know, basically, the way that a two-dimensional array works in memory is you take the sort of rectangular conception of the data, and you linearize it by concatenating the data on the end of itself, so that sort of in the same way that you would read H-gaps in shell sort, the actual, like the columns are interspersed throughout a linear array. However, with a double pointer, they are all pointers to probably different and disparate areas of memory, so they don't need to be the same size. So, malloc m times size of int. There we go. And just for the sake of interest, we can print foo at I is equal to some pointer value, well, I and foo at I. There we go. Just to be able to, oh, my gosh, I've been teaching Python again. There we go. So, you know, and then you can, I believe you can even address, yeah, you can even address these using double array index notation for reasons that we're going to see once we get into the actual meat of the lecture. But, get out of here, fly. But yeah, so that's how you would allocate such an array. And then, of course, you would have to have symmetrical operations in order to free all of this data, because, you know, that's how life works. You should always give back that which you have borrowed. And then once you've deallocated every element, you can deallocate foo itself. Does that make sense? Am I making sense to you guys? So the obvious follow-on question from that is, okay, sure, but what you've asked us to do is implement shell sort, so what is the intention there? How is this applicable to the shell sort algorithm? Well, for those of you who were paying... Oh, I have got a question. What if you deallocate foo before the inner elements? Well, so deallocating foo doesn't... I do not believe that deallocating foo deallocates everything that it points to. Not with, like, regular free. There might be, like, some sort of, like, souped-up advanced version of free that, like, goes through and deallocates everything that free points to. But, generally speaking, this is the safe way. I'm not, like, I can't guarantee that all of the data that you've allocated is going to be freed unless you actually give free those allocated pointers. So, I could be wrong about that, actually, but this is the safe way to do it. So the question of application to shell sort, right? I'm not normally this generous when it comes to giving hints on assignment questions, but I understand that shell sort is a reasonably complicated algorithm, so I'll give you guys a couple of hints. So, if you take a look at this sort of visualization of the H-gaps, which is the approach that I'm sort of suggesting that you take with respect to shell sort, it's not actually necessary to approach it in this manner, but this is, I think, a way that's, like, coincides with the way that it's explained in the slides, etc., etc. If you notice, the slicing operation, the H-gap finding operation, is a matter of taking this linear array and then producing a matrix according to the H-gap length. Well, the problem that you have is that the size of this matrix in terms of its length and width, that is dynamically, that's something that occurs dynamically at runtime. So you have to use dynamic allocation in order to get that size. Although I suppose, in theory, you could just allocate a whole bunch of memory and work inside of that memory, but that's not an efficient solution because that uses way too much memory. You would need to have like a square space of memory the size of the entire array, so you're allocating the square of the size of the array in memory in order to perform this algorithm, which kind of defeats the whole purpose. So the problem is that in these cases, these arrays are sort of designed to be sliced into perfectly rectangular matrices when you perform the slicing operation. I chose the number 12 because it does that easily. However, if you have a array length which is not evenly divisible by 1 plus the h gap, you will not end up with a rectangular array here. You will end up with a ragged array in the same manner as this guy, right? Except it'll be like, 5, 5, 5, 4, or something like that. So that's how dynamic allocation of the pointers that are in the array of pointers, that array of pointers would correspond to, those would be your H slices, and like you'd go along the columns to pick out your subarrays. But anyway, hopefully that's hopefully that's useful to you guys. We should probably move along with our lecture material for today. So, when we were talking last, we were talking about pointer arithmetic. Because pointers have concrete numeric values, it does actually make sense to perform arithmetic on them. And because it makes sense in the sense that useful operations can be derived from arithmetic on pointer or on memory addresses. In fact, that's what an array is. That's what you're doing when you are indexing an array, is you are performing pointer arithmetic. That fact has just been hidden to you by the syntactic sugar of the array indexing operation. So, the thing that we were pointing out in the previous example is that the addresses of each of the elements of an array are offset by the bit width of the type of the array, where foo is an int array and bar is a short array. We have 4-byte offsets here and 2-byte offsets here in terms of the memory addresses. And this also, I think, for the first time reveals to us that our memory is addressed by the byte rather than by the word, as you might think if you thought about it. So, notice in the previous slide how foo's memory addresses are 4 bytes apart and bars are 2 bytes apart. The array is continuous memory, and each element is allocated the size of the base data type of the array. If we wish to perform pointer arithmetic to traverse the array, we need to know how big the steps are. Well, technically speaking, we don't actually, but we, in the sense of, like, if we were to implement the compiler, we would need to know how far apart to go. Operators can mean different things when applied to arguments of different types. This is a concept which we are already familiar with in C, if we consider floating point versus integer division. It is a point that's also quite familiar to us from Python. Consider the different uses of the in operator in different contexts. In a for loop, it means one thing. In an if conditional, it means something completely different. So our old friend, the increment operator, plus plus, when applied to a pointer, will actually automatically take on the size of the data type it's operating on. So you get to the next pointed to value in an array by using plus plus, and you go backwards by using minus minus. Pardon me. So question. I was checking the Wikipedia page on shell sort. In their examples of age gap 5 means we skip 4 and take the 5th element. Ooh, go according to the slides. If there is a conflict between information in the slides and information in the external world, please use information in the slides, because that's what I used to generate the answers for the assignment. So, here's an example of traversing an array with pointer arithmetic. Let's imagine we have a character array foo, entitled dated reference. We then have foo pointer, which is, that should have the address. Oh wait, no it shouldn't. Foo is already an address, right? So you don't need the address of operator here. While foo pointer is not equal, while the dereferenced version of foo pointer is not equal to the null character, print the character at foo pointer at the address specified by, you dereference foo pointer to get the character, and then we plus plus. And remember, the increment operation plus plus, when placed after the operand, takes place after the calculation of the statement that the plus plus occurs in. So foo pointer is being incremented after the print statement. In this manner, we get dated reference with all of these braces around each character. So there you go. There's also a way to configure this so that it also does the null character, which is kind of cool. If you, like, do it as a do while, or... no. I don't know. Anyway. So there we go. The following are valid operations on pointers: plus plus, minus minus, plus minus, plus equals, and minus equals, as well as, regular assignment. In each of these cases, the number you are adding or subtracting to or from the pointer is implicitly multiplied by the bit width of the data type. So, for example, if pointer points to an integer, then pointer plus equals 4 would move the pointer by 18 bytes. That is, the actual memory address value would be increased by 16 rather than 4, since the bit width of int is 4 bytes. This is a small amount of arithmetic that C performs in the back end, so that the number here can be in your brain like whole variables, rather than, like some weird scheme where you're reading partial variables. Pointers may also be subtracted from one another, but only meaningfully if they point to the same array. So, pointer A minus pointer B yields the number of array elements difference between the two pointers, not the number of bytes difference. And if you imagine, if you have pointer A pointing to some address inside of the array foo, and pointer B pointing to some address inside of the array bar, and those are, offset in memory, those aren't the same array, like the position in memory of those arrays is going to be random, essentially random, based on like when the program is being executed. So if you imagine that subtracting one pointer from another is going to yield you consistent, reliable, and informative results, you are wrong, sir. So, a word to the wise. In the previous example, tracing a character array, we used our knowledge that strings are null terminated to set a stopping condition for our loop. If you notice, we stop when the character pointed to is null. Pointer arithmetic can easily place a pointer outside the bounds of its original data structure. You can imagine if you were going backwards up an array rather than forwards down an array, there's no null character at the beginning of a string, so there's no way from telling what the character values are when to stop. And in an integer array, there's no indication in the data itself when you should be stopping. Just like everything else to have to do with arrays in C, you are the sole responsibility for making sure that the data that is being read from is actually allocated data falls to you, the programmer. There is no built-in protection against out-of-bound pointers, so we can easily use them to assign to memory outside of the array bounds. So you can imagine if you are putting values into memory addresses that are stored by pointers, and that pointer is pointing to something that's not been allocated, interesting things can happen. This could overwrite other variables, cause segmentation faults, and many other types of troubles. While desktop operating systems they'll protect against this sort of thing a lot of the time, embedded systems do not always have these sorts of protections, especially the older ones. So be careful. Ubuntu will catch that type of thing and prevent you from damaging things. Embedded systems do not always have these types of protections built in because, it takes code to do something like that. It takes a more robust kernel. And in some cases, the embedded systems that you're using will not have operating systems at all. You will just be programming instructions directly onto a processing core. And if that's the case, then you can very easily, overwrite memory that might even be something like your firmware. I actually Googled around to see something like, can you overwrite firmware with pointer problems, and I didn't find anything interesting, but hypothetically I think it's possible. Wildcard pointers. We kind of already talked about it, but I'll go over it briefly again. There's a type of pointer called a void pointer. Void pointers are wildcard pointers. Any type of pointer can be assigned to a void pointer, and a void pointer can be assigned to can be cast as any type of pointer. So it could be an int pointer, a char pointer, a float pointer, any pointer. You can think of it as a wildcard or a generic pointer. It's generic in the sense that the pointer data type carries with it the bit width as the primary information about it. This is actually also the case for normal data types like int. The most important and interesting thing about ints with respect to the compiler is that they are 4 bytes. The same thing applies to pointers. So essentially, a void pointer is a pointer with none of that information. It does not have a specified bit width. So because it doesn't have a specified bit width, the compiler would have absolutely no idea how much of a chunk of your memory to give back as a dereferencing operation. Therefore, dereferencing void pointers is an invalid operation. It cannot be performed. In order to dereference a void pointer, you have to first cast it as some data type. That tells the compiler how many bytes of data to barf back up at you in the process of a dereferencing operation. Yes. Are there any questions? Bloop, bloop. So let's talk a little bit about some miscellaneous operators. Equality and relational operators work on pointers. I mean, they do have concrete numeric values, so of course, why wouldn't equality and relational operators work on pointers? Relational operators are only meaningful if the pointers refer to the same data structure, same rules as subtraction. And equality comparison with null is quite common for pointers, because pointers are often given initial values of null, or pointers are given null if a malloc operation is unsuccessful. So equality comparison is actually quite common, much more common than relational comparison. I'll just finish the slide and then take that question. Array indexing is actually syntactic sugar for pointer arithmetic. So whenever you are indexing an array using square brace notation, this is specifically and directly equal to dereferencing the pointer plus whatever the number here is. It is a pointer dereferencing operation. You didn't know that until now, but that's true. That is 100% fact. That is not fake news. Therefore, it is also possible to index pointers in the same way as arrays. So, if you would prefer to use indexing notation rather than dereferencing notation, as long as you are aware of the equivalency between the two, it doesn't matter which of the two you use. One of the few differences between pointers and array identifiers is that array identifiers may not be assigned to. So they are considered constant pointers, right? They're sort of implicitly declared as read-only pointers. Whereas when you declare it as a pointer rather than as an array identifier, you are opening up both read and write privileges. So let me take that question. Could you show an example of how to use a void pointer? If you're okay waiting for the next set of slides, there's a really good one when we talk about string operations. So if it's okay with you, I'm just going to let the course answer that question rather than take the time to answer it right now. Can we do pointer arithmetic on void pointers? Good question. I don't see why you wouldn't be able to. Maybe. I don't know. Let's see. Void pointer bar is equal to null. Yeah, sure. Let's say bar. No. Let's do it afterwards. Oop. This void pointer bar is equal to the address. We'll set it to the address of foo. There we go. Let's say bar plus plus and see if the compiler complains at us. Slides. Topic 5, code. Terminal. What did I call this? Double point. GCC wall double point .c. I've got errors. Near. Implicit declaration of malloc. Whoops. I suppose I should probably include the standard library then. Ha ha ha. See if that helps. Okay. Expected expression before int. Int I undeclared. this way? Maybe it's that way. Yeah. Okay, so when you're casting pointers, the asterisk goes after the type. Oh, yeah, in there. Yeah, so this incrementing that doesn't actually do anything. So let's just take a look what bar actually is. That might be informative. Ah, jeez. I've been programming in Python again. Aha! So when we increment bar, incrementing on a pointer arithmetic on a void pointer is just modifying the value in the manner that you would expect on like an integer. The multiplicative factor is 1. So it does work. I wouldn't recommend it because you will misalign yourself with respect to how the operating system allocates data. So I wouldn't recommend it, but it's possible. For the void pointer, why would we want to use a void pointer? Because if we need to cast it to dereference it, that would mean that we already know what data type it is, so why not just use that type of pointer in the first place? Some functions are general for a lot of data types. So we're going to see this when we take a look at some of the stuff coming up in topic 6. Some of the functions in there return values of different data types depending on depending on how you use the function, and in those cases you have to cast the pointer that's returned to different data types depending on the situation. So, but the function itself will return a void pointer because it can return a pointer of a number of different data types. How does a read-only pointer affect the ability to edit the first element of the array foo? They both have the same memory address. Well, okay, it's different. Let me go to... There we go. So, the difference is this piece of memory right here, the pointer variable itself, that is read-only. This will always point here. This cannot be changed. However, if you were to dereference it, this memory, this piece of memory has full read and write privileges enabled. So you can modify this cell, but you can't modify that cell. So hopefully that answers your question. Yes. Cool. Good questions, everyone. You guys are so good. I'm just pleased as punch to have you guys in my class. So, so we move right along to the idea of function pointers. And I know this looks like a big section, but a lot of it is code. So hopefully we'll be able to get it through it in the 10 minutes we have remaining in class. Things that are true. Pointers point to memory addresses. Functions are stored in memory. Ergo, pointers can point to functions. In C, a function name is really the starting address of the function's instructions. Pointers to functions may be passed to functions, returned from functions, stored in arrays, assigned to other function pointers. Pointer arithmetic really doesn't make any sense at all for it, though. So, for those of you who have brushed against the functional programming paradigm, we are now in the territory of passing functions to functions as arguments of functions. So this is kind of this is a head scratcher. You kind of have to wrap your head around it. Although this is the shell sort algorithm that I'm requesting that you write on on assignment 3 also involves that algorithm takes a function as an argument. So this is how you do it. In some programming languages, most notably Haskell, passing functions as arguments to functions is commonplace. In fact, it's so commonplace that in Haskell, passing something to a function is such a common operation that it is mapped to spacebar, which is interesting. Just like most things in C, C can do this too. You just need to be willing to use some elbow grease. So, consider the following function prototype. Void bubblesort int work. This is the array that we will be sorting via bubblesort. Size is the size of the array, obviously. And then there's this interesting one. Int star compare takes int a and int b. So the third argument is declared as a pointer to a function, taking two int arguments and returning an int. So you can see, like, this is a miniature function declaration inside of our function declaration. There's, if you leave out the fact that this is, if you don't consider this for the moment, if you were to replace this with just a identifier, that would look exactly and precisely like a function prototype without the semicolon. So compare is the identifier that we are giving the function, and the parentheses bind star to the function name. So the difference is, if we left out these braces here, what we would end up with is int star, an integer pointer, right? This binds the pointerization operation to the function name itself, and that is how you create a function pointer. Once you have passed a function into a function, the passed function is used in the exact same manner as you would use any other function. You just use the function name that's specified in the argument. Yeah. Without these braces, this would be interpreted as an integer pointer. So let's consider the following Big Bubblesort example. It's not important to go through every detail of this, just the highlighted bits. So in the function prototype, we kind of already talked about it, but it's int star compare, int a, int b, takes a and b. So essentially, you are able to pass as an argument, as the third argument of the bubble function, any function that matches this set of arguments and return value. Otherwise, it's a syntax error. So, this is main. In main, when we call bubble in main, we can call it with either ascending or descending. Ascending and descending are functions which are defined later on in the file. Ascending is, both of them are basically just we're just renaming less than, and greater than as operations. But it modularizes it. It makes it more, to some degree, it hooks this type of thing up to our modularization goal with respect to software development. So it makes it more, makes it easier to change in the future, easier to maintain, if that makes sense. So when we invoke bubble, we invoke it with a function that matches the declaration in the function prototype. when we are implementing bubble itself, we again reproduce the function argument in the as the third argument in the same way as the prototype, as you might imagine. And when we invoke the function, we invoke it again using the braces and the star. So we are dereferencing the function pointer in order to pass things to the function. So there you go. The output of this program, we have this array which is unordered, although it looks reasonably ordered. That gets reordered into ascending order if we wish to sort, if we give it the ascending command, and descending order if we give it the descending command. That's the other thing about this algorithm. Oop, oh my goodness. Control, there we go. Basically, it prompts the user for whether to sort in ascending or descending order, and then does so based on, the scanf result. So, what's going on here? On line 7, the third argument of bubble is declared as a pointer to a function taking 2 arguments and returning an integer, which is being used as a boolean in this example. On lines 16 to 44, the user is prompted whether to sort in ascending or descending order. Based on their choice, either the function ascending or descending is passed to bubble. On line 60, to invoke the passed function, we once again bind the dereferencing operator to the function name with parentheses. Lines 76 to 86 are the definitions of ascending and descending, and have no special syntax. The only requirement is that they have the same type signature as the function pointer. So there you go. It is also possible to have arrays of function pointers. Just like everything else, we can organize function pointers using arrays. This is how you would declare that. Int, we use parentheses to bind the pointerizer operator to f, and we indicate the types of the arguments. We then can provide a list of functions. To declare an array of function pointers, once again, we bind star to the identifier with parentheses. Additionally, a list of argument types is provided immediately afterwards. The 3 ints above indicate the function's typing information. In this case, all functions in the array accept 2 integer arguments and return an integer. Array sizing follows normal rules. Since function identifiers are pointers to functions, we can use them directly to initialize the array. There you go. Here is an example of that being used in the wild. We have function prototypes for functions 1, 2, and 3. These are given as the initialized value of the f array. The user is prompted for a selection. That selection is then used as the argument, or the index of the function, the index of the array containing the function definitions, and whichever one of those is used is then passed the choice as well. And you can see these are, reasonably stupid functions that are just producing different text, but, you can imagine that this would be useful in the context of programming something like a text adventure. So, there you go. And that's it. That is our slides on pointers. If there are any questions, please enter them into the chat, and I would be absolutely happy to answer those for you guys. upload the C code for the two examples. What was that? Doublepoint.c? Which ones are you talking about? Are you talking about the ones in the slides or this double point that I did? For shell sort, does the number of swaps depend on the h-gaps? Holy heck, does it ever. Yes. The number of swaps very strongly depends. I don't actually have them. I don't think I do. Give me a second here. Maybe I've got... Maybe it's in here. Chapters. No, nothing in there. Those are just solutions to the textbook questions. Nope, I'm pretty sure I don't have... Maybe this is it. Ho-ho! I found them. I found them indeed. I have them. I will upload them. You have asked for a thing which shall be provided. So there you go. Oh, shoot. Did I not include that information in these? Okay. For the assignment, I will post the h-gap sequence immediately. Yeah. I will post the h-gap sequence immediately. Sorry about that. I just used the most recent one in Wikipedia. So, Wikipedia shell sort. I used this one. I used the one here, the unknown experimentally derived one. However, I will make an announcement about that. So there you go. Incidentally, if you guys are at all interested, these are the slides that I've been basing I've been using. You know, at the beginning of my slide decks, I say that they're adapted from Deedle and Deedle. Well, these are what I've been adapting from. I just want to show you this briefly so that you might appreciate all of the effort I've been going to improve your educational experience. I would post these, but there's absolutely no point. They're terrible. Yes. So, this is like literally. It's like word for word from the textbook. And one of the interesting things to note about this is that my slide deck on pointers is 63 slides, and all of the malloc stuff is stuff that's not even in that chapter of the textbook. And so, how many slides do I have on malloc? It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So actually 50 slides in terms of the slides from the textbook, that is equivalent to 182 slides. So you're welcome. How would the final sort work? Well, like the whole point of shell sort is that the final sort is just insertion sort, right? But if you have performed all of the H-gap sorts, then no element is further away than it. Well, in the case of this H-gap sequence, no element is more than four positions off of its correct place. So insertion sort can be performed really quite quickly and easily. But yeah, I take your point that maybe the H-gap plus 1 problem might be biting me in the keister right now. But just have it work. Have an implied 0 gap here, and then you've got the solution that I've based the autograder on. Yeah, by my slides, the final sort is a sort with an H-gap of 0, and that is insertion sort. Sorry about that. To be completely honest with you, the slides that I produced for shell sort are based on primarily that Wikipedia article, and it is always possible that when it passes through my brain, I have an imperfect impression of how an algorithm actually works. I have made a small and technical inaccuracy, although largely the algorithm is correct. I would ask you to please follow my small and technical inaccuracy in your implementation of shell sort, such that your solution will line up with the assignment solution that the autograder is based on. For subsequent offerings of the course, I will clean that up and make it not. I will fix that technical inaccuracy, but sort of it's difficult to fix it at this point because like all the materials have been deployed. I provided you with bubble sort instead of insertion sort. It doesn't change the number of swaps, but is it an issue? It's not an issue since the number of swaps is the same, but basically the only reason I provide you bubble sort is because A, the number of swaps don't change, and B, bubble sort is much shorter. And you know, I was concerned that you might. Oh my goodness, I forgot to post the assignment solutions the last time I was asked. Jesus. Thank you for the reminder. Yeah, just use the function that's provided. That's the one that I used in the solution, so. Yup. Anyway. Hopefully. I'm gonna sneeze. Woof! You're welcome, Omar. Cool. Anyway, you guys have class to get to, and I want lunch, so I guess I'll talk to you guys. I'll be having office hours in this channel in 1 hour's time. In the meantime, please have fun